In this video, we are going to look at a second example using the app and looking at the relationship between blood flow and blood pressure and viscosity and vessel radius and all of those things. So as I read at the top of the screen here, it asks me to set my blood pressure at 100. So I'm here in the app and I'm taking the slider, setting the blood pressure to 100. Next, it asks me to put the viscosity at 3.5, which is where I have it from my previous problem, and the length at 50, which I also have for the previous problem. This time we are going to be looking at vessel radius, and the first vessel radius is 1. So I'm going to slide this down to 1. Now, as I'm going through this, I want to actually change my graph, because the first graph that we saw, which was the straight line, was the graph for pressure. So I'm going to click over here and look at the graph for radius. So first thing I notice on this graph is that the points are still increasing, so that's something, but there's concavity now. It's concave up instead of a straight line. And the points are not nearly as close together. So pressure, we had points really close together. The radius here, the points are a little bit more spread out in our graph, and that's because our radius, we don't have as many delineations there, like blood pressure jumped from 100 to 120, lots of numbers in here. Here we're only moving from radius of 0 to 6. So that's why the points are more spread out. The number that I want to record is up here at the top. So the flow rate under this first scenario is 0.2244. And so I'm going to record that in my chart. 0.2244. So then I'll go and do the next one. So for this next one, the radius is to be 2, so I slide that up, and I see that has a huge impact on flow rate. So now it's 3.5904. And I go through the app and I do the rest of these. So I move it to a radius of 3, and that gave me a flow of 18.1764. And a radius of 4 gave a flow of 57.4463. And finally, a radius of 5 gave 140.2497. So first thing I want to do is just observe. So I observed that the vessel radius got bigger each time, so vessel radius going up. I look at my flow rates, they got bigger each time as well, so they are going up. So after that initial observation, I'll take a look at the question. As a person ages, he or she will experience arteriosclerosis, which is the thickening and hardening of the walls of the arteries. Arteriosclerosis decreases the radius of the vessels. How will it impact blood flow? So I know from what I observed that if we would increase the radius, we would increase the blood flow. So this is saying that we're going to decrease the radius, and so that is going to decrease blood flow. So if an increase increases it, a decrease will decrease blood flow. So then it asked me which of the 4 will be constant. Well, the constants are those 3 at the top that I set as constants. So this time we were holding the pressure constant. That's the one that we varied last time. We were holding the viscosity constant. And so viscosity is set to be 3.5, and we didn't change that throughout the example. And length is constant at 50 for the entire problem. Then they asked me, well, what is varying? So the 2 things that are varying are the 2 things in my chart. So what I saw as varying is the radius varied each time. I kept changing that. And the flow rate varied each time. So then I asked, well, what type of variation is going on? And so I have to think about what we talked about as the class when we talked about proportional. And we noticed radius increased, flow increased. So when they both increase together, that is direct variation or directly proportional. So now it asks me to compare my graph to that in question 1. They have the same variation relationship but different graphs. Explain how they are different. So I am going to bring my app back here so that we can look at this, even though we did talk about it right at the very beginning of the video. So the first one, question 1, we looked at pressure. The graph was increasing, but it had a constant rate because it was a line. And the second one, radius, the graph is still increasing because it's uphill, but it is increasing at an increasing rate. So the increasing rate means that the slope is getting steeper and steeper, which is causing it to have that concave up shape and to be a curve instead of a straight line. So explain how they are different. So pressure, that was our first one. Increased blood flow. At a constant rate. But radius increased blood flow. At an increasing rate. Letter F, the French scientist found that blood flow varies, and I'm going to fill in the word directly here because we notice both increase, which is the direct variation or directly proportional relationship, with the fourth power, so that's super important, of vessel radius. We're to define variables and write our equation. So I'm going to use R, lowercase r, for radius. I'm going to use uppercase R for rate. You can use different letters if you find the two R's to be confusing. So the lowercase r is my domain, which is where I would often use X. The uppercase R is the range, which is where I would often use Y. So I want to start this problem out with uppercase R for flow rate equals, it's directly proportional, so it's K times, that's always in every directly proportional relationship. And then I want to use the lowercase r for radius, and I want to put an exponent of 4 because of the work of the French scientist who told us that it's with the fourth power. It tells me then to use any pair of numbers to find the constant. I'm tempted to use the first one because that's what I typically do, but the math for that one is super simple. So I'm actually going to use the second one just to show you the more complicated math in case you run into something else that's more complicated. So using the pair of numbers from the second row of the data that I wrote down. The flow rate, uppercase R, is 3.5904. And it is equal to K times the radius of 2 to the fourth power. So the math here is just one extra step from what we have done before. So that extra step is that we actually have to take out a calculator and type in 2 to the fourth power, and we find that that is 16. So simplifying, I have 3.5904 equals K times 16. And then we know that the opposite of multiply is to divide, so I'm going to divide by 16 on both sides. Sorry, that looks like a 76. It's supposed to be a 16. These cancel. And I type this into my calculator. So 3.5904 divided by 16, and I get 0.2244. And that's what K equals. Now, you might notice that that was the first value that we had found in our chart, and that's why I picked to use the second row so that I could show you the math involved, because that first one worked out to be incredibly easy, and so sometimes that's almost worse to look at as an example when it's that easy. Letter G says use the pair of numbers to find the constant, so that's what I just did over here to the side. That was letter G. So letter H, use your equation to predict the flow rate when the vessel radius is 7. So I'm going to use my equation, uppercase R equals, instead of K, I'm putting in the constant 0.2244. Instead of R, I'm putting in 7. And I do have to use that exponent of 4 to get my answer. So I'm able to type this into my calculator, and I get a huge number because it's a huge increase in radius. And that with that exponent of 4, that has a really big impact. So 538.7844. So that is how we always set up a directly proportional idea with the multiplication. And we always use directly proportional when both items are increasing. This problem had the extra exponent in there, which our first example did not.